Welcome to Learn Civil Easy. Today we begin a new subject, Irrigation Engineering, and we begin where every water project has to begin with the water itself, where it comes from, where it goes, and how much of it we can actually catch. This is Unit 2, Hydrology. Let me start with a question. When rain falls on your roof, on your road, on your field, where does it go? Some of it evaporates straight back into the air. Some of it soaks into the ground, some of it is caught on leaves and never reaches the soil at all. And some of it, only some of it actually flows away into a drain, a stream, a river. That last part is the only part an engineer can catch and use. It has a name, it is called runoff. And almost everything in this unit is about finding out how big that share is. All of that water is moving in a circle, and the circle has a name. The hydrological cycle. Watch it build. Here is the sea, and here is the land rising away from it. The sun heats the surface of the sea, and water leaves it as vapor. That is evaporation. The same thing happens from lakes and rivers and wet soil on the land. Plants add to it, they draw water up through their roots and release it through their leaves, and that is called transpiration. All this vapor rises, and as it rises, it cools. It condenses onto tiny particles of dust and forms clouds. The droplets grow until they are too heavy to stay up, and they fall as rain or snow or hail. That is precipitation. Some of it is caught on leaves and roofs and never reaches the ground. That is interception. Of what does reach the ground, some flows over the surface into streams and rivers, surface runoff, some soaks in infiltration, and some travels down past the roots to the water table and becomes groundwater, which moves slowly and eventually also reaches the sea. And then it starts again. Now notice two things about this diagram because examiners ask for both. First, what drives it? Two things only: solar energy, which lifts the water up, and gravity, which brings it down and moves it back to the sea. Second, and this is the sentence to remember, the hydrological cycle has no beginning and no end. It is a closed circulation, which means the total quantity of water on Earth stays effectively constant. Water is never created and never destroyed here. It is only moved and changed from liquid to vapor and back. What changes is where the water is and when it is there, and that water in the wrong place at the wrong time is the problem every dam, every canal, and every reservoir in this subject is built to solve. Before we leave the diagram, 3 words from it that carry marks. This dashed line is the water table. It is the upper surface of the saturated ground, and the simplest way to think of it is this: sink a well anywhere here, and the water will stand at exactly this level. Above the water table, the soil pores hold both air and water. That region is called the zone of aeration. Below it, every pore is completely full of water. That is the zone of saturation, and it is the groundwater reservoir. Students very often draw the cycle and forget the water table. Do not, it is usually worth a mark on its own. Now, let us turn that picture into arithmetic. Apply conservation of mass to a catchment over some chosen period, and everything in the diagram becomes one equation. Precipitation equals runoff plus evaporation plus transpiration plus infiltration plus or minus the change in storage. Now, over a long period, say a full year, the change in storage becomes small enough to ignore, and every term except runoff is water we have lost, so group them, and the equation becomes this: runoff equals precipitation minus losses. Write that down because that single line is the whole of this unit. Every definition we meet from here is either measuring the first term, estimating the second, or finding what is left over. 2 words that get used as if they were the same and are not. Precipitation is the family. It means all forms of water reaching the earth from the atmosphere. Rain, snow, hail, sleet, drizzle, dew, frost. Rainfall is one member of that family, precipitation in the liquid form. In India, rainfall is very nearly all of the precipitation, so we use the words loosely, but in an examination define them separately. It is a free mark. Now, how is rainfall measured? Here is the definition. Rainfall is the depth of water that would stand over a horizontal impervious surface if none of it ran off, evaporated, or soaked in. Read that again. The depth. Rainfall is a depth in millimeters. It is not a volume. If you want a volume, you must multiply by an area. And here is the conversion worth memorizing. 1 millimeter of rain over 1 square kilometer is 1000 cubic meters of water. Rainfall is measured at a point by a rain gauge, standing at a rain gauge station in the open clear of trees and buildings. On level ground with its mouth held horizontal, there are two families. Non-recording gauges, the Simon's gauge is the standard one, are simply a funnel discharging into a bottle. Somebody comes once a day, usually at 8:30 in the morning, pours the catch into a measuring cylinder and reads it. Cheap, simple, no power needed. Recording gauges, also called self-recording or automatic, write their own record continuously. There are three types to name: the tipping bucket, the weighing bucket, and the float or natural siphon type. Now here is the distinction. The examiner is testing. A non-recording gauge tells you how much rain fell. A recording gauge tells you how much and how fast and when. Only a recording gauge gives you the intensity, and as we are about to see, intensity is what decides whether rain runs off at all. So, runoff, here is the definition. Runoff is that part of the precipitation which flows over the land surface and through the stream channels to reach the outlet of the catchment. Follow the chart. Rain falls. Some is intercepted by leaves and roofs and evaporates from there. Some evaporates from wet ground and open water. Some is trapped in puddles and hollows, that is called depression storage. Some infiltrates into the soil where part is held as soil moisture in the root zone and taken up by crops, and part percolates down to the groundwater. And what is left flows over the surface. Those first four are the losses: interception, evaporation, depression storage, and infiltration. Learn that list of four. And what survives them, plus the water that comes back later from underground, is the total runoff measured at the catchment outlet. Water reaches the stream by three different routes, and the difference between them is speed. The first is surface runoff, also called overland flow, straight over the ground into the channel, arriving in hours. This is the one that causes floods. The second is interflow. It infiltrates first, then travels sideways through the upper soil, arriving in hours to days. The third is base flow. It percolates all the way down to the water table and then seeps into the bed of the channel, taking weeks or months. So total runoff equals surface runoff plus interflow plus base flow. And grouping the first two as direct runoff, total runoff equals direct runoff plus base flow. Base flow is the reason a perennial river is still flowing in May, months after the last rain, that water fell during the monsoon and has been traveling underground ever since. A stream with no base flow dries up between storms, and we call it ephemeral. Now we need a number that connects rainfall to runoff, and that number is the runoff coefficient, written C. It is simply the ratio of runoff to rainfall over the same catchment and the same period. C equals R over P, so runoff equals C times P. It has no units and it always lies between 0 and 1. Watch what it means physically. When C is close to 1, the surface is practically impervious. Everything that falls runs off. Steep bare rock is about 0.9. When C is close to 0, the ground is very pervious. Almost everything soaks in sandy soil. With heavy brush cover is about 0.1. In between, stiff bare clay around 0.6. Cultivated loam around 0.3. Do not memorize a table of numbers, learn the pattern instead. C rises as the ground gets steeper, barer and more impervious, and falls as it gets flatter, more vegetated and more pervious. Let us use it. A catchment of 100 square kilometers receives an average annual rainfall of 1200 millimeters. The runoff coefficient is 0.35. Find the runoff and the volume of water available. Step 1. The runoff depth. R equals C times P 0.35 times 1200, which is 420 millimeters. Step 2, and this is the step that people lose the mark on, convert that depth into meters. 420 millimeters is 0.42 meters. Step 3, the volume, depth times area. 0.42 meters times 100 million square meters gives 42 million cubic meters of water. Notice what happened at step 2. If you multiply millimeters straight into square kilometers, you will get an answer 1,000 times too big. Write the conversion on its own line every single time. What decides how much of the rain becomes runoff? The factors fall into two families, and naming the two families before you list anything is worth marks on its own. First family, the characteristics of the rainfall. The type of precipitation. Rain runs off at once, snow is stored until it melts. The intensity, and this is the most important single factor of all. Once the intensity is greater than the rate at which the soil can absorb water, everything extra becomes runoff. The duration, the longer the storm, the wetter the soil, the more runs off. The areal distribution, the direction of storm movement. A storm traveling down the valley piles the water up and gives a higher peak. Antecedent rainfall. If it rained last week, the soil is already wet and runoff is high. Second family, the characteristics of the catchment. Its size, its shape. A fan-shaped catchment gives a high early peak because every side drains to the outlet in about the same time. A long narrow one gives a lower, later, flatter peak. Its slope, its soil and geology, its vegetal cover, more cover, less runoff, its land use, and this one matters enormously. Roofs and roads and paving are impervious, so as a city grows, its runoff rises sharply, and that is exactly why urban flooding gets worse every year. Drainage density, and any lakes or tanks which store the flood and release it slowly. So let us stop there and take stock. The hydrological cycle, no beginning, no end, driven by the sun and by gravity. Runoff equals precipitation minus losses, and the four losses are interception, evaporation, depression, storage, and infiltration. The runoff coefficient C equals R over P, always between 0 and 1. And the factors that decide runoff come in two families, the characteristics of the rainfall and the characteristics of the catchment. Now one question is still open. A rain gauge measures the rainfall at a single point, but every calculation we do needs the rainfall over the whole catchment. In the next video, we will answer exactly that with the three methods, the arithmetic mean, the Thiessen polygon method, and the isohetal method. Study notes and a model answers paper for this lesson are on our Telegram channel. I will see you in the next one.